My name is Michaela Cartwright. My student number is CAR16003542. This assignment is all about the sport analysis in netball. The main joints of a netball chess pass are shoulder, elbow, wrist and fingers. The types of joints is the ball and socket, hinge joint, condyloid joint, ball and socket. The bones articulating the joint is the clavicle, vertebra, scapula, ilium ribs, articular capsule, spine of scapula and acromion. The preparation phase is using the sagittal plane, is flexion of the elbow caused by concentric contraction of the bicep. This means that there is a relaxation of the tricep. Horizontal abduction at the shoulder caused by contraction of the latissimus dorsi. The execution phase using the segmental plane is from supination to pronation using circumduction caused at the wrist, is using the flexocarpal as the agonist and the flexocarpal ulnaris as the agonist. Extension of the elbow caused by concentric contraction of the tricep is the agonist muscle, and the bicep relaxes, which is the agonist muscle. The horizontal abduction at the shoulder caused by contraction of the pectoral major and minor. The fixator, which holds the joint stable, is the biceps, triceps, quadriceps, hamstring, soleus and external carpi ulnaris. So the acute phase of the cardiovascular system is the heart rate, anticipatory response. The heart rate increases and then levels at a steady pace. The cardiac output increases. The vasodilation of blood vessels to and from the muscles occur when supplied to the working muscles with glucose and oxygen and any removed wastes. Vasoconstriction of blood vessels to and from the digestive system. This is the liver and kidneys. Blood pressure increases and then levels off at a steady rate, just like the heart rate. When you're exercising, the heart beats fast to get oxygenated blood to the working muscles as fast as it can without the SA node. The heart won't know when to beat fast or beats at a normal pace, so this controls the rhythm. Respiratory response. The first one is increase in heart rate and breathing rate. Breathing rate increases from about 18 breaths per minute to up to 80 breaths per minute due to exercise. There's an increased demand of oxygen from the activated tissues. The O2 is required by the aerobic energy systems to produce ATP to provide the energy needed for the muscles contraction to happen. An increase in breathing rate then increases the O2 intake and the O2 removal in the body. Marib and Keeler suggest that the respiratory system takes in oxygen, which is required for the metabolism, and it excretes carbon dioxide. The increase in tidal volume is the expiratory reserve volume. Extra volume of the air can be expelled from the lungs. Inspiratory reserve volume, which is the extra volume of air that can be breathed in the lungs. The reserve volume, the extra volume of air which remains in the lungs after the athlete has expired from the air from the lungs. Vital capacity, or force vital capacity, the maximum amount of air the athlete can breathe without breathing in the maximum amount of air. Functional residue capacity, the amount of air in the lungs after the normal expiration, which is breathing out. This is the balance of the tendency to the lungs to recoil inwards, then the walls of the chest to pull outwards. Total lung capacity is the air which is in the lungs by the end of the maximal inspiration. Brochard L suggests that the tidal volume is different for every athlete depending on the climate and how much exercise they do, as well as the weather and many more. So all positions either use aerobic or anaerobic glycolysis, which will be explained later on. The goalkeeper would use anaerobic glycolysis. The goal defence would use aerobic glycolysis. The wing defence would use anaerobic glycolysis. The centre would use aerobic glycolysis. Wing attack would use anaerobic glycolysis. Goal attack will use aerobic glycolysis. Goal shooter would use anaerobic glycolysis. Davidson A and Trivera G suggests that the netballer changes direction and or movement every 0.5 seconds. ATP, which is andesine triphosphate, is the first energy system the body starts with. ATP is a source of muscle contraction. The chemical chain for ATP is A-P-P-P. When the bond is broken using enzyme exothermic reaction, the energy released from the reaction is called antipase. ATP lasts on average for 0 to 3 seconds, depending on how well trained the athlete is. Anything after 3 seconds is classed as ATP, which isn't energy, but requires an endothermic reaction, which is energy, to return back to ATP. ATP's energy may ultimately be transformed into the electronic energy for a reserve impulse for the mechanic energy of non-contracted muscles. The PC system uses phosphocreatine. The chemical chain for PC is P-C, which is phosphate-creatine. With the bond creatine kinase in the middle, this is the bond which breaks to release the energy called an exothermic reaction. A couple reaction is the product of one reaction which is then used to complete another reaction. For example, ADP plus P plus energy equals ATP. Then the extra C, creatine, waits to resynthesize with the next P. 1 PC is the same as 1 ATP. The PC system lasts for 3 to 10 seconds on average. This depends on the athlete's gender, age, where they perform their sport, such as outdoor or indoor. Greenhalgh PL suggests that the PC system is a coupled reaction which releases energy. Anaerobic glycolysis, or known as the lactic acid system, is for 10 seconds to 3 minutes on average. Carbohydrates are consumed and converted into the liver into glycogen. This when it stayed in the liver as reserved energy until the bond needs it to be used. Therefore, glycogen gets broken down into glucose by the enzyme GPP, which is glycogen phosphorylase to then get broken down into provugic acid by the enzyme PFK, which is phosphofructokinase. From this reaction, the body gets 2 ATP to use for the muscle's contraction, and pruvic acid gets broken down and turns into lactic acid by the enzyme LDH, which is insignificant oxygen. So the athlete needs to start to perform a lower intensity exercise to start to re-increase oxygen supply. Aerobic glycolysis is the pruvic acid in the presence of oxygen getting turned into the COA, which goes into the acetyl COA. The Krebs cycle, which is acetyl COA, combines with oxalated acid, which then makes citric acid. CO2 and hydrogen is removed with which synthesizes 2 ATP to then make oxygenated acid. This lasts for 3 minutes plus. Many cells ranging from microbes to lymphocytes use aerobic glycolysis during rapid perfection. Hydrogen is moved from the citric acid to make oxygenated acid. FAD plus NAD, hydrogen carriers. FADH plus NADM, when hydrogen is present. Electron transport chain, ETC. Hydrogen passes through the hypochondria. Cryptase folds into hypochondria and gets split into ions H+ and electrons E-. Electrons E- is where we use the energy to resynthesize 34 ATP ions. H+ gets into H plus O2 equals H2O. 38 ATP total, which is a 1:38 ratio. The point that lactic acid affects performance on average is 2 to 4 millimoles is when obla is reached, which is the lactic acid starts to affect performance. Lactic acid lowers the pH in the muscles. This means enzymes are denatured, which means they can't resynthesize ATP, so the athlete feels really heavy. The athletes are trained, they can delay obla by long-term effects of the cardiovascular system.